CERN is the largest European organization for physics research and one of the largest in the world. That's taking place on the border between France and Switzerland. And there's very long tunnel in there where they're taking protons and they're smashing them close to the speed of light. And when they do that, all of that energy, when those protons smash together, actually turns into heavier particles because of E equals mc squared mass energy equivalence. And so it's a pretty amazing, operation that they have there, and it's a great case study for us as we consider how scientific research is done. When we consider the scientific method, we've learned these kind of the pattern. First, make your observations. Second, formulate and objectively test the hypothesis. Third, interpret the results. And then fourth, state the conclusions. And in real life, how this works, is very fluid. So, as we think about our operations at CERN, we see that, and we'll continue to explore that. And then there's no single procedure that scientists, a scientist doesn't show up to work and say, okay, I'm going to do step 3 today. It's very fluid, but all scientific research follows this basic pattern. Orders of magnitude is a way to look at values and compare values in a very convenient way. And the way this works is we look at the value rounded to the nearest power of 10, and we see how many zeros there are. So let's say that we take a look at this distance from the Earth to the Sun. That's a pretty large number and in meters, and we can put this in terms of a power of 10. So what we do is we take this number and we take the log of this number, and we get 11.17. And so in terms of orders of magnitude, the height of this, or the distance this is 10 to the 11th meters. So let's say that we had a theoretical situation here with a building that's extremely tall here. I'm not sure what I was doing when I was making that one, but I think I just wanted to compare the different numbers. So so let's try this one where we have a building that's 65,202 meters, and we want to figure out the order of magnitude of this building and compare that. So go ahead and try that, and when you're ready to check, you can hit play to continue. Okay, so we take the log of this value, and we'll get 4.8. So the orders of magnitude with this would be 10 to the 5th. So what we can do is we compare the orders of magnitude. How many more orders of magnitude is the distance from the Earth to the Sun, and we subtract those values. 10 to the 6th is the difference, and so that's 6 orders of magnitude. So we can compare things based on how many orders of magnitude. Okay, so how many heartbeats in orders of magnitude will you have in a lifetime, assuming 85 years? And so I'm going to have you try this. You're going to take your heartbeat for a minute and then try to figure out the total number of heartbeats that you would have, assuming that you had a lifetime of 85 years, and we have how many days there in a year. And see if you can do that. So go ahead and pause the clip and try to do that and get the orders of magnitude of how many heartbeats you have, and then we can look at my example here. Okay, so for me, the example here, I've got 70 beats per minute, and we have 60 minutes, and then 24 hours, and then 365.25 days, and 85 years, and so a total number of 312,946,2000 beats per lifetime. If I get that in orders of magnitude, I get that, and so 10 to the 9th beats would be my estimation there. If you set up a bracket, which is probably be wise, having 70 beats per minute, and you want to get all the way to this here. So we have 60 minutes in 1 hour, 24 hours in 1 day, and then 365.25 days in 1 year. And then we can multiply by 85. And so that's what happens. We're multiplying across the top 70 times 60 times 24 times however many days to get how many beats per, in this case, this would give us beats per year, because hours would cancel out, days cancel out, and we're left with the years, so beats per year, and then we multiply by 85 to get beats per lifetime there. So estimation problem solving, again, can be very helpful using orders of magnitude estimate values. And I'll have you read this about using estimating to solve problems. So go ahead and pause the clip, and when you're ready to continue, hit play. So Enrico Fermi is estimating the strength of the atomic bomb using the Trinity test. We can use the orders, or he used the orders of magnitude to figure out how much energy that the TNT made compared to the bomb there, and so we can do that as well. And so this is a classic problem here that we can use where we use the estimation to determine something. So how many piano tuners are there in Chicago? So this is one of the classic Fermi problems, and we can use logic and use estimation to do this. So let's say that we know how many people are living in Chicago. So we have that, 9 million people. On the average, there are 2 persons in each household, and roughly 1 household in 20 has a piano that's tuned regularly. We can think through that. Pianos that are tuned regularly are tuned on an average about once per year. It takes a piano tuner about 2 hours to tune a piano, including travel time. Each piano tuner works 8 hours a day, 5 days a week, and 50 weeks in a year. So from these assumptions, we can compute the number of piano tunings in a single year in Chicago. So we have that many people divided by 2 persons per household, and then 1 over 20 households have a piano, and then times 1 piano tuning per year. And that's how many piano tunings on estimate we can assume in Chicago per year.
So now that we know the number of piano tunings, we know that each person can do 4 per day, and based on how long it takes, 2 hours each, including travel. So they can do 20 per week, and so therefore 20 times 50. If they work 50 weeks, each person can do 100 per year. So based on that, go ahead and determine how many people that would be. So go ahead and pause the clip and do that, and when you're ready to check, you can hit play to continue. All right, so we have that many tunings that we need, and we divide by 1,000. There should be another 0 there. Divide by 1,000. We get 225 people that would be required for that.
Okay, so in this one, we want to determine how many grains of sand would it take to fill the volume of the Earth. This is another example. So we want to think through, what are some of the things that we're going to need here? Well, we'll need to know the radius of the Earth to be able to figure out, how much volume there is. And we'll also need to know, the size of an average grain of sand to be able to see, how the Earth is filled up. And so if we think about we know the volume of the sphere is 4/3 pi r squared, and the approximate grain of sand here is going to take a space of about 1 millimeter, by 1 millimeter by 1 millimeter, taking the diameter. Now we could use, if you think about grains of sand, being all stacked up against each other, you're going to have some of that empty space because, it's going to be pushing against the other sides. And so we can assume that there. And so, yeah, let's see if you can figure out from here how many grains that would take to fill the Earth in orders of magnitude. And so go as far as you can, and when you're ready to continue and check if you get stuck, or if you want to check, you can hit play to continue. So go ahead and pause, and then when you're ready to continue, hit play. Okay, so we know that the total area of the Earth is 1.51 times 10 to the 14th. And if we get an estimation of the orders of magnitude there, it'd be 10 to the 14th. And then from there, we've got, we can look at the total area divided by the area of a little one here. And you could have taken the total amount, if you wanted to there. And we'll get something like the 1 times 10 to the 23rd grains is what we'll need. And so we have our value there of about how many grains that we would need. So in this one, if everyone on Earth held hands at the equator, how many times would the loop go around the Earth? And so we know some values. Well, we need to know the values that we need, right? So how many people are in the Earth, and then also the radius of the Earth. So let's assume 7 billion people, and we'll assume the radius of the Earth is 6 times 10 to the 6 meters. So I'll have you try to figure out this one as well. So go ahead and pause the clip and give this a try, and when you're ready to check, you can hit play to continue. Okay, so yeah, how wide will we hold our hands? That's something else that we would need. And if you assumed about 1.5 meters across, you could do that. And so we know how many people, we know how long that this loop would go around, and we know the circumference of the Earth, 2 pi r. So that's the circumference of the Earth. So if we take the total length divided by the circumference of the Earth, we would go around about 279 times around the equator. Okay, so now we're going to talk about the fundamental units. And there are 3 fundamental units that we're going to discuss right now. The first one is time. And the way that we distinguish what time is a little bit interesting here. And you might wonder kind of why that we do this. So this was updated in 1997. And the second is the duration of 1,992,631,770 periods of the radiation corresponding to the transition between the 2 hyperfine levels, the ground state of the cesium-133 atom. So what in the world does that mean? So if you might remember from chemistry, you have the different states. You have the ground state, and you have these more excited states. And the electrons can go up and down in these states. And so what they did is they wanted something that was completely objective, where you could have a statement and say, this is what a second is. And what happens is this is how many times in a second that this electron will go up and down between the 2 hyperfine levels in this atom. And that's going to be standard no matter what. You don't have to have something in a building, saying this is what a second is, like some kind of clock or something. And so you've probably heard of the different atomic clocks, and that's basically what's happening there. They're using the element and measuring time based on the change in those levels, and so it makes it very, very precise. Length is another one that they've updated relatively recently, say 1984, and they define the meter as the distance light travels in a vacuum in 299,792,458 seconds, with time measured by a cesium-133 atomic clock. So why in the world would we do that? Well, instead of having a physical meter stick and then trying to base everything off a physical meter stick, which has problems, right? Because that physical meter stick could change over time. And so what they did is they figured out a way. They said, okay, if we take a laser and we shoot it across and we measure how much time it takes to go across for a meter, we can have this standard throughout the world. We don't have to have a physical meter stick, and it's standard across the board. Now, there is a problem with mass, and there's a great Veritasium video. It's called the roundest object on Earth, and I highly recommend looking that up. I think that's how the channel's spelled. And it's a great discussion on why we're still stuck with mass, where we actually have a physical kilogram. And they're working to get something where it's like time and length, where you don't have to have a physical object. But for right now, that's what we have. We have the International Prototype Kilogram. Looks like this, and it's made of platinum and iridium. And over time, it's actually the mass of that kilogram has changed slightly, and so they're trying to get an objective way to say, you know, actually have a statement instead of a physical kilogram locked up in a vault. And that's what we have to this day, that we base the kilogram on that.